In this video, the pruning strategies and association mining to correlation analysis will be discussed. Sub-item set pruning. If a frequent item set X is a proper subset of an already found frequent closed item set Y and support count of X equal to support count of Y, then X and all of X descendants in the set enumeration tree cannot be frequent closed item sets and thus can be pruned. As in the problem, suppose a transaction database has only transaction A1 to A100 and another transaction set A1 to A50 and the minimum support count is min sub equals to 2. The projection on the first item A1 there is a frequent item set A1 up to A50, that is 2 times colon 2 based on the item set merging optimization, because support of A2 equals to support of A1 to A50 equals sign 2 and A2 is a proper subset of A1 to A50. There is no need to examine A2 and its projected database. Similar pruning can be done for A3 to A50 like. Thus, the mining of closed to frequent item set in this data set terminates after mining A1 as the projected database. In the depth first mining of closed items, at each level there will be a prefix item set X associated with a header table and a projected database. If a local frequent item P has the same support in several header tables at different levels, we can safely prune P from the header tables as higher levels. Consider an example: the previous transaction database having only transaction A1 to A100 and A1 to A50 where min sub equals sign 2, where A2 in A1's projected database has the same support as A2 in the global header table. A2 can be pruned from the global header table. Similar pruning can be done for A3 to A50. There is no need to mine anything more after mining A1's projected database. Besides pruning the search space in the closed item set mining process, another important optimization is to perform efficient checking of each newly derived frequent item set to see whether it is closed. This is because the mining process cannot ensure that every generated frequent item set is closed. Important optimization is to perform efficient checking. Perform two kinds of closure checking. Superset checking checks if this new frequent item set is a superset of some already found closed item sets with the same support. Second, subset checking checks whether the newly found item set is a subset of an already found closed item set with the same support. For efficient subset checking, we can use the following property. If the current item set SC can be subsumed by another already found closed item set SA, then number 1, SC and SA have the same support. Second, the length of SC is smaller than that of SA. Number 3, all of the items in SC are contained in SA. Patterns are interesting. Most association rule mining algorithms employ a support confidence framework. Although minimum support and confidence thresholds help weed out or exclude the exploration of a good number of uninteresting rules, many of the rules generated are still not interesting to the users. Unfortunately, this is especially true when mining at low support thresholds or mining for long patterns. This has been a major bottleneck for successful application of association rule mining. Misleading strong association rule. Let game refer to the transaction containing computer games and video refer to those containing videos. Of the 10,000 transactions analyzed, the data show that 6,000 of the customer transactions included computer games, while 7,500 include videos and 4,000 included both computer games and videos. Minimum support 30%, minimum confidence 60%. Support value of computer game 4,000 divided by 10,000, 40%. Confidence value of the videos, the 4,000 divided by computer games 4,000 divided by 6,000 equal to 66%. The probability of purchasing videos is 75%, which is even larger than 66%. In fact, computer games and videos are negatively associated because the purchase of one of these items actually decreases the likelihood of purchasing. The support and confidence measures are insufficient at filtering out uninteresting association rule. This leads to correlation rules of the form if A then B, support, confidence and correlation. A correlation rule is measured not only by its support and confidence but also by the correlation between item sets A and B. Lift is a simple correlation measure. The occurrence of item set A is independent of the occurrence of item set B if P of A union B equals sign P of A and P of B. Otherwise, item sets A and B are dependent and correlated as events. Lift of A, comma B can be calculated as P of A union B divided by P of A and P of B. Lift of A, comma B less than 1 is A and B are negatively correlated. Lift of A, comma B is greater than 1, A and B are positively correlated. Lift of A, comma B equal sign 1 and A and B are not correlated, they are independent. It assesses the degree to which the occurrence of one lifts and the occurrence of the other. Same problem, the contingency table has been created. A 2 by 2 contingency table summarizing the transaction with respect to game and video purchases. Probability of game equals to 0.6, probability of video equals to 0.5, P of game, comma video is 0.4, then 0.4 divided by 0.6 into 0.7, 0.89. 0.89 is less than 1, so game and video are negatively correlated. The above contingency table now shown with the expected value. Observed values are outside the bracket. Inside the bracket, expected values are given. The correlation analysis using chi-square. Correlation analysis using chi-square. Observed value minus expected value whole square divided by the expected value. The result is after calculation 555.6. So the value is greater than 1 and the observed value of the slot game comma video is 4000, which is less than the expected value 4500. Buying game and buying video are negatively correlated. So chi-square equals to 0 is independent. Chi-square greater than 0 is correlated, either positive or negative needs